Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch more. Today we're doing multivariable calculus. We're at the end finally of chapter 1, which is partial derivatives. This will be section 1.8, which is the last section, Lagrange multipliers. An alternate way of finding the max-min values for surfaces, and then we can also do this with constraints as well when we start interacting, and then we'll give you some ideas of when that would happen and when you want to look at what's happening here. And then we use Lagrange multipliers to find max-min values for functions of 2 or 3 variables. Good, let's do that. Okay, for the idea of Lagrange multipliers, first we're going to go back to, we're going to switch dimensions a couple times on top of everything else, but it would be the easiest way to explain what's going on for the first time. First of all, to explain Lagrange multipliers, what we're going to do is we're going to find the explicit equation of a tangent plane to, or on the way to doing that. We don't have to put it here, but we're going to get from that a way of dealing with and deriving Lagrange multipliers, or the idea. First of all, what I need is, he's secretly not there, but what we're going to notice is we have a function of 3 variables f. We're going to look and set that equal to k and look at their level surfaces. We get a surface S. At some point p, we're going to get a tangent plane to that surface now, but we want a magic equation, or specifically to know who the normal vector to that plane is, specifically when we do not a willy-nilly surface in 3 space, but one that comes from a level surface of our curve. Doing that, we notice that to find the equation of the tangent plane to S at this point, x naught, y naught, z naught, we remember that in vector calculus, our position can be parameterized with the parameter t, and then we get a position function x of t, y of t, z of t, and then the derivative of that is the direction in the direction of the tangent line to our curve gamma at the point P. And then, so we get the coordinates are x prime, y prime, z prime with respect to time. How are we going to use that? Now what we're going to do is, having that information, we want to notice that who is this guy actually in purple. I've already drawn it there, but who is it? Implicitly differentiating this now using the chain rule with respect to time t. We're going to differentiate this. The left-hand side is 0 because k is a constant. Implicitly differentiating f with respect to time now by the chain rule gives me the partial of f with respect to x, dx dt, the partial of f with respect to y, dy dt, and the partial of f with respect to z, dz dt. What does that give me? I have to notice now cleverly, who are these guys? This one and this one and this one are the gradient vector, and this one and this one and this one are these guys, Leibniz notation, Newton's notation, but if you notice and remember that, oh, so that looks like it's the dot product of gradient vector and this r prime guy. And that's exactly what's going to happen. So for that equation of that tangent plane to a level surface, we notice that from the equation that we moved up before we rewrite it, we notice that 3 of the components were the gradient vector and the other 3 were the vector in the direction of the tangent line. So we notice that if we write them like this, we get the equation gradient dot product r prime. What that does for us is that says that the vector that is normal to that plane, because this is laying in the plane, the vector in the direction of that plane, or normal to the direction of that plane, is in fact the gradient vector. Therefore, we also notice that the gradient vector is perpendicular to r prime. How does that help us with Lagrange multipliers? Now what I'm going to do is step down to 2 dimensions so I can draw more accurately what's going on, so we can look at level curves instead of level surfaces, but it'll be the same idea, just 1 dimension lower, and we'll see where this idea of Lagrange multipliers and finding max or min values is involved in the gradient, this gradient business and tangent level surfaces. This is Jasper, she came to say hi. So now what do we have? When we want to tie Lagrange multipliers to the scenario that we were doing last time, bye kitty, what we want to do is, we went down a dimension so I can draw level curves instead of level surfaces. So these are going to be the f1s, f of xy equals L, and this one is the single constraint that we have where g of x, y equals k. So to do this game of Lagrange multipliers, what they're saying is we're trying to maximize the function f subject to another constraint g of xy equals k, or g of xyz equals k, whichever one dimension we're doing. We'll do examples of both. Long story short, this amounts to finding the largest value L such that these curves intersect. For other values of L, we may have, if this is L equals 3 and L equals 4 and L equals 5 and so on, we see that L equals 3 intersects the g of x curve, intersects that one, but at more than one point. We want a tangent essentially, or just touching, so that they just intersect. We want the largest L such that they intersect. And that's this one, L equals 4, is the idea of what we're looking for. What that's going to say now is, because of that, it says that at that point, F and G share a common tangent line and therefore a common normal line. And so in this case, it's one dimension lower, but in the higher dimension, it would be the tangent planes, and then they're going to share this. And what that's saying is, from the previous remark to tangent planes and lines to level curves and surfaces, we're going to get that the gradient of F is parallel to the gradient of G because they're sharing it. Because they're tangent, the normal line to this curve is the normal line to this curve, and so they're the same. And what that means is, even though they may have different magnitudes, linear algebra, they're definitely going the same direction, and that means they're parallel. And what does it mean? Pavlovian reflex, when vectors are there, what it says is not these functions, their gradients are parallel. And what does that say when two vectors are parallel? They're multiples of each other, and this is what we're going to call the multiplier. The Lagrange multiplier is the lambda in the equation. From this derivation and from trying to maximize this guy with the constraint this, we're essentially looking for the largest L that this happens, that they intersect just touching. Because of that, we get that their tangent lines and therefore their normal lines are equal to each other, planes in the higher dimension. Because of that, we see that they're parallel, and their gradients are parallel, and therefore they're scalar multiples of each other. This says, long story short, the gradient of f of x naught, y naught is a multiple of the gradient of g at x naught, y naught, or x naught, y naught, z naught. We're in a higher dimension. This is what's happening. And then we also have the extra constraint, this constraint equation, plus now another equation that says cleverly, if that's what we're looking for from this scenario and deriving that, we get this equation, and these two things become the method of Lagrange multipliers. Let's try that out. Explicitly, to state the theorem before we give the method of Lagrange multipliers for 2 and 3 dimensions, or functions of 2 and 3 variables, I'll state the theorem for a function of 2 variables. It's analogous to a function of 3 variables. So Lagrange multipliers. Who are the Lagrange multipliers? Lambda is the Lagrange multiplier, and this theorem says they exist. Basically, sort of, we have to guarantee, can you always play this game, or maybe there is no largest L such that that happens. What this is saying is it always happens, you can do this, and then therefore you can use the method of Lagrange multipliers to find max and min values for functions with constraints. If I have a function is different, or f and g are differentiable functions of x and y, or x, y, z, and f of x, y has a local max min, we're trying to maximize or minimize f on a constraint g of x, y equals 0. I know equals k equals 0, don't worry about the subtlety. If that happens at a point a, b, and third, if the gradient of g is not 0 at a, b, then there always exists a Lagrange multiplier, lambda, such that the gradient of f is equal to a multiple of the gradient of g. And we also have the extra constraint that g of x, y will equal k. Then what we're going to do is we're going to use the Lagrange multiplier equations, and then we're going to use the constraint equation to solve for the maximum and minimum values for our function with given an extra constraint. Let's give explicitly the algorithm or the method of Lagrange multipliers, and then we'll do an example. All right, the method of Lagrange multipliers one more time. To find the max min values of a function f of xy subject to this constraint g of xy equals k, or a level curve, we do the following. 1, we write out the Lagrange multiplier equations. These are going to be nonlinear equations in 2 variables or 3 variables, or 3 and 4, because we don't know what lambda is either. Anyways, then what we're going to do is we're going to solve for x and y using the constraint somehow. Beg, borrow, and steal. There's no methods, not like linear algebra. And then once we have those, hopefully, you go to the last value and you evaluate f at the points you found in this constraint business. The largest one is your maximum, the smallest one is your minimum, or if you only get one, you'll see whether there's a maximum or a minimum using that constraint. You'll find out. Let's try that for a function of 2 variables, a baby one. Example 1, this will probably be the only example in this video. You have to try a few, note to self, because every time I do this I get nonlinear equations in my constraints. Hopefully they're nice where I can solve and get myself out of it immediately, but there's no systematic do this and you'll get yourself out of a nonlinear system of equations. I don't know. No one else does, so they're going to give you baby ones, but you have to try a few. I'm going to start off with really simple partial derivatives 1 and 2, so then they're constants at least, and then I can solve for x and y, yeah, and then we're going to step it up. So in the next videos we'll go step it up to complications, then I'll step up a dimension x, y, z, and then we'll play that a few times. You should practice a few of these. And then you haven't even seen, we can add more than one constraint. We'll add 2 constraints, or lambda and beta, and then you're going to need more, yeah, kappa and what? Greek letters, more Greek letters. For this one specifically, I have a function f, x plus 2y. We have an ellipse, 3x squared plus 4y squared equals 3. What I'm going to try and find is this guy and this guy, max and the min values on that ellipse, subject to this, or for f of xy on this ellipse, which is my constraint. This means what specifically? First of all, before we start, you want to organize this for this yourself. This says g of xy is 3x squared plus 4y squared, and that says g of xy is equal to 3. There's my constraint. Can you see it now from the mumbo jumbo? There's my f, there's my constraint, g of xy equals 3. Now what do I do with that? Step 1 of Lagrange multipliers. Write out the Lagrange multiplier equations. To do that, you need what? The partial derivative, or the gradient essentially. So you need the partial derivatives of f to do that, and the partial derivatives of g, because we're going to set the gradient of f equal to the gradient of lambda, and then write down my constraint as my extra equation. So I'm going to get 3 equations and 3 unknowns, lambda, x, y. How are we going to do this? First of all, fx luckily is 1, and fy in this case is 2. Good, I've got those guys. Then what do I need? The partial derivatives of these guys. It's a little bit worse, but not too bad. This says gx is equal to 6x, and gy is equal to 8y. Not too bad. What does that give us? That says if I have that the gradient of f is equal to lambda, the gradient of g, that tells me that now I get equations. This says that 1, 2 has to equal lambda times 6x, 8y. Those are the gradient vectors. Scalar multiplication, aha, now I get to use it for vector calculus. This says that I get 1, 2 is equal to 6 lambda x, nonlinear, 8 lambda y, nonlinear. And what does that give me? 2 vectors are equal in linear algebra if their coordinates are all equal. So then I get a system of 2 equations and a third equation, which is my constraint. And I have 3 equations and 3 unknowns, but nonlinear. What am I going to do with this? This gives me 1 equals 6 lambda x, and this gives me 2 equals 8 lambda y. And then I also have g of x, y, which is 3x squared plus 4y squared equals 3. I have 3 equations. Let's move that up and see what happens here and try to find the max and min value. Step 2, what do we want to do? We want to find x and y using the constraint. What does that mean? Basically, first of all, lambda is not 0. We have to solve a nonlinear system of equations, and there's no systematic method for doing this, so practice a few and get some ideas from how to do this. How do I know lambda is not 0? Well, I erased it, but we had 1, 2 should equal lambda 6x 8y. And if lambda was 0, that would say 1 equals 0 and 2 equals 0 by scalar multiplication, and this is bad. So lambda is not equal 0. And then what we can do is I can say that if I want to do this, a lambda is going to equal 1 over 6x, and lambda is going to equal 1 over 2 over. I'm solving for lambda in these equations also. Now can you see that I can solve for x and y cleverly, and because I can set them equal to each other. From this, what I see is 1 over 6x equals lambda equals 1 over 4y. And I can cut out the middleman. That says y is equal to 3 over 2x. What does that do for me? Basically, this says there's infinitely many solutions. X could sort of be anything, but y depends on is 3 over 2x. And then what I'm specifically going to do is, right now that says x, there's infinitely many solutions, x could be anything, but how are we going to get it? We're going to use our constraint now, and that's what it means. You find x and y using the constraint. So I use the Lagrange multiplier equations somehow cleverly, depending on how they're nonlinear, to find an expression usually for y depends on x and something like that. And then now what do you see what I can do is I can solve that by putting y equals 3 over 2x into there. I get a nonlinear equation in one variable x, and at least I can try and factor a nonlinear equation, which is going to be a polynomial in this case. That's the idea in general, but these can be crazy depending on which kind of surfaces you're trying to look at intersecting or the constraints. Long story short, from the first two, or from the Lagrange multiplier equations, I found y is 3 over 2x. I'm going to put that into the constraint equation to solve for x and then therefore y, because I know what y is. Because we now know from the first two equations that y is 3 over 2x, I put that into the constraint equation, and simplifying, I notice that I get 12x squared minus 3 equals 0, or I can take a 3 out of both of those. I get 4x squared equals 1. I don't know why I moved that over to factor it out, but that happened. And then if and only if what, we're at least solving a quadratic. X squared is equal to 1 over 4, or x is equal to plus or minus 1/2. Immediately from that, what do I get? This says y is equal to 3 over 2x, which is equal to 3 over 2 plus or minus 1/2, which is equal to plus or minus 3/4. That gives me the points respectively corresponding. What? That means I get the points 1/2, 3/4, and the point negative 1/2, negative 3/4. Those guys. Once we have those guys, what do I have to now do to that? Step 3 is, once I have the points, I have to evaluate f at those values and see which is the bigger and the smaller. Let's do that. Finally, once we have those values of x and y from our constraint business, I put those into f of x, and I find out that at 1/2, 3/4, I get the value 2, and at negative 1/2, negative 3/4, I get the value negative 2, and what that says is this is a minimum, and this is a maximum for my function at those values right there and right there. So for my function x plus 2y on the ellipse 3x squared plus 4y squared equals 3, it has a maximum value of 2 and a minimum value of negative 2 is what that's saying. How do we do this? One more time to recap. Step 1 is set up the Lagrange equations. How do we do that? We take the partial derivatives of f and the partial derivatives of g, and we set the gradients equal to each other, and we get these equations. And then we get the extra constraint equation. From that, step 2 is solve for x and y using these, and then put that into here cleverly into the constraint and find values of x and y. We found 2 values of x and y respectively. Step 3 is put them into the function and find the largest value and the minimum value. Please subscribe right here, hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. See you next time.